So solids now. Okay, okay guys, now in the last videos we have studied the effect of the shapes and the intermolecular forces in the boiling points and the loss of other properties, Clausius-Clapeyron equations. So we have solved the numerical problem also using on the basis of the Clausius-Clapeyron equation, right? If you remember that the Clausius-Clapeyron equation, we use the two temperatures, two pressures, and use the delta heat of vaporization, and then a very useful property we studied there, right? Then we also studied that in the Clausius-Clapeyron equation, if we have the pressure data and the temperature data, we can plot them, right? Log of the pressure and the reciprocal of the temperature. If we plot that, we can easily have the delta heat of the vaporization also we can find out. So, and after that we have studied in last video that what is the what kind of the intermolecular forces has responsible for more higher boiling points. The stronger intermolecular forces results the higher in the boiling point, and the weaker intermolecular forces result in the lower boiling points. And if two equal similar type of the molecule, we can say the shape also, right? And the shape also determines the higher or lower boiling point, right? We studied in the last video that if shape is more elongated, the cylindrical, if its shape provide you the higher contact area, then it can have the higher dispersion force and the higher boiling point. And if the molecule provides the lower contact area, then that results into the lower dispersion force, which finally results in the lower boiling point. So we studied that in the last video. Now in this video we will discuss about the property of the solid states, and finally we will discuss the very important property of the phases, which is the phase diagram of the liquid or of the substance. We will discuss basically on the basis of the water phase diagram, and you will learn a lot about the phase transitions and different point on the phase diagrams. We will study that on the coming video. Let's go on that. Now let's think about the solids. Now we have done about the liquids. Now let's go to the solid. Cooling reduces the velocity and the kinetic energy of the molecule to the point where the kinetic energy can no longer overcome the intermolecular attractive force. Then that is the solid. Okay, what the solid happens? So solid also, so once the liquid has molecules are moving, okay, if their velocity is more than, if velocity is more than intermolecular force, so means that these two are together, right? If the velocity is enough to pull them apart, it becomes the gas. And in certain amount, if the velocity is same as like the intermolecular force, this will be liquid. Okay, if the velocity of these two is more enough, that is enough to take them apart, right? Take them apart, then it liberates and becomes gas. If the velocity is similar as like the intermolecular force, they cannot liberate the velocity, they can move but not enough to liberate, then that is a liquid. However, they can move, right? Let's see, this can move here, but that velocity is not enough to liberate, not enough to break down that force. Means that whatever the force is here, that is similar as like the velocity. This velocity is not enough to pull them apart, then that is the liquid. But if a velocity is way smaller than the intermolecular force, then that is a solid. That's why the velocity and the kinetic energy of the molecule to the point where the kinetic energy can no longer overcome intermolecular attractive force, then they are solid. When the attractive force between molecules becomes so strong, then the random motion stops the solid form. Then random motion stops. If the more intermolecular forces is very strong, so that it don't let to move, then that is a solid. But the intermolecular forces is not enough to stop that velocity, if stop that random motion, then that is either liquid or gas. So gas is the velocity is enough to liberate, enough to break down that intermolecular force barrier. Okay, but the liquid, the velocity is not enough to break down the intermolecular force barrier, but still they are in the random motion, they are liquid. Okay, in the solid, intermolecular forces are so strong, it is enough to stop the motion. Then that is the solid. So solid don't have the random motion. Liquid has random motion and the gases have random motion. So in the gases, enormously large amount of the velocity, that velocity of the molecule is huge, so that all the gas particles force is negligible. Its velocity, they molecules go so much apart to each other, that high velocity, and that high velocity creates the kinetic energy. That kinetic energy is too much higher than the intermolecular forces. That's why in case of the gas, we just calculate the kinetic energy. We don't measure actually what is the intermolecular forces. So the intermolecular forces is way small than the kinetic energy. Kinetic energy due to the velocity of the particles, right? In case of the gas, kinetic energy is too large, way higher than the intermolecular forces, the energy due to the intermolecular forces in the gas. In the liquid, kinetic energy is not enough to take the particle apart. However, the molecules are moving, but the intermolecular forces also a reasonable amount. That's why intermolecular forces keep them held together at a certain distance. That is the liquid. That's why if you give the heat, liquid can evaporate, because the liquid can get more kinetic energy, so that the kinetic energy can break down the barrier of that intermolecular forces. So in case of the liquid, if you study the liquid, you have to study kinetic energy plus intermolecular forces. That's why liquid state are very, very difficult to study. Still, we have to find a lot about the liquid state. Liquid state are very difficult to study. We have to study kinetic energy also, intermolecular forces also. But the gas, this is the liquid. In case of the gas, only the kinetic energy, because this intermolecular forces is not enough to keep these molecules together. That's why intermolecular forces is very, very small, and the velocity overcomes the velocity, gives the kinetic energy. That kinetic energy overcomes the intermolecular forces. That's why kinetic energy. And if you think about the solid, no kinetic energy, only intermolecular forces. So now let me write that very important property. Solid, we just study IMF, intermolecular forces. Velocity is 0. Velocity is about 0. Velocity of the molecule is 0. So no velocity. These intermolecular forces binds them so tightly, they cannot move randomly. No random motion. No random motion. Okay. That's the solid state. And the liquid state, if you think about the liquid state, both intermolecular forces plus kinetic energy. That's why liquid states are very, very hard to study. They are difficult. They are still, we have to find a lot. The scientists are still working on that. So intermolecular forces and kinetic energy, both you have to address together. So it is very complex. That's why the liquid states are most complex states. So intermolecular forces also, kinetic velocity is not 0. Velocity is not 0. Still they have the velocity. That's why kinetic energy also not 0. In case of the solid, kinetic energy equal to 0, almost 0. And the gas has no intermolecular forces, only the kinetic energy. So the intermolecular forces are almost 0. So that's why gas is pretty defined. It's easy just to study the kinetic energy. The solid, it's easy just to study the intermolecular forces. But the liquid is very complex. That's why out of these three phases, liquid is the most complex state in scientific field. So because it has IMF also, kinetic energy also. that, okay. Now let's think about some types of the solid, like ionic solid, right? They have the high melting point. For example, this is the example. Molecular solid, okay, they have the dispersion force and the low melting point they have. For example, ice, aspirin, example. Polymeric, they are polymer, giant molecule, right? For example, rubber and plastic, they have also low melting point or cannot be melted, or soft or hard, depends, okay. So network solids, a very large number of atoms connected by covalent bonds, that is the network. For example, they are very hard, very high melting point, or cannot be melted, network. For example, the diamond, quartz, they are very hard and it is very hard to melt. And amorphous solid also, they are randomly arranged. For example, the network, they have the pretty well defined lattice structure, but in case of the amorphous, they are randomly connected together, okay. So mostly they are soft, that's the reason. They can be made to flow also, but no melting point. So for example, suits, tar, glasses, etc. So the metallic, there are other metallic solids. They are metal atoms surrounded by a cloud of the electrons. They are the metallic solids, okay. They are also soft also. They are very, very hard also, right? They are sometimes they are some in the liquid form also, like the mercury, right? So for example, gold, iron, copper, they are the metallic solids. So there are different types of the solids, many types of the solid, okay. So now let's study the phase change. Phase change, you have a 3 phases, solid, liquid, phase. And if you increase the temperature and the pressure, if you change the temperature and the pressure, a state of the matter with a state change the state, and that is said to be the phase change. Phase means either liquid phase or gas phase or solid phase, or you can, if you go beyond that, the plasma phase or like others, okay. So basically in our chemistry we think about there are 3 phases: solid, liquid or gas. The phase change means if you change the temperature and the pressure couple, means the pair of the temperature and the pressure, and it may have the different phases. So it may change the phase if you change the temperature and the pressure. So if you phase change means a change from one physical state to the other physical state, gas to liquid, liquid to solid, solid to liquid, okay. And the mixture also, right? There are another intermediate phases also. That is mixture of the solid and the liquid, that is also one phase. Mixture of all these 3, that is also other phase, okay. That is the critical point also, we will say. We will go in a phase diagram and you will understand better, okay. Now let's see that here. This is the phase diagram of our water. So phase diagram means it is a diagram which tells you about the phase of the material at a particular temperature and the pressure pair. That is the phase diagram. If you think about, so now what this phase diagram has, in the y-axis you have a pressure, okay guys, pressure in y-axis, and you have a temperature in x-axis. So what is happening, let's see that this phase diagram is this form. This is one point, and after this is another point here, okay. And this is the one boundary, this is other boundary, this line is other boundary, and this is the boundary, this is one other boundary. And look at that, this is the liquid state. Let me give different color, and that's why it is easy to understand, okay guys. This is the red, this is blue, okay. Let's say, okay, now let me see that this is the red boundary, blue boundary, okay. And now let me the green boundary or this boundary also, okay. This is another boundary, okay guys. This is blue boundary and a pink boundary and a green red boundary, okay. So look at that, this whatever this region, all these points have certain temperature pressure, right? Let's say this is the temperature. If you pick out this point here, this point has certain temperature, you see, certain temperature and certain pressure, right? This much is the pressure, this much is the temperature. At this place, this whatever this, the pink dotted region, that is for the liquid. Okay, and this region, let me give the different color for that. Okay, and blue, and this blue region, this blue dotted, this region, it is a solid. Okay, now let me give you black, and this black region, this whole black region, you see, this black region, this is the gas. This is gas. What does it mean? If you have this temperature and this pressure, this point, right? This much is the pressure, this much is the pressure, this much is the temperature, your liquid will be gas. Your substance, your phase will be gas. If this is the temperature and this is your pressure, this is the pressure, this temperature and that pressure, this is here, oh okay, this is the solid, right? What will be this? This point is what? This pressure and this temperature. If you give this temperature and that pressure, and that phase will be the gas phase. So let's think about this pressure. Let's say that is 1000 atm, 100 atm, suppose. This is the pressure and this is the temperature. Let's say this is if that is 100 and this is, suppose that this is 90. For that particular substance, 90-degree temperature and 100 atmosphere pressure, what is the phase? Now let's take this 90-degree vertically. It goes here and oh okay, this is a liquid, right? At 100 atmosphere and 90 degree is the liquid. So this is 5 degree centigrade and the 10 atmosphere pressure, like this is a solid. So these are the phase diagram. Phase diagram tells you what is the phase at particular temperature and the pressure. Now let's see that. This is the water, okay. This is the phase diagram for water. Phase diagram for different substances is different, okay. So first of all, let's see, this is the green boundary, blue boundary and red boundary. And all these regions, if the temperature and pressure couples, temperature and pressure pairs from this orange region, that will be gas. For example, 300 degrees centigrade and 1 atmosphere. This is the 1 atmosphere. Okay, let me encircle that. This is 1 atmosphere. At 1 atmospheric pressure and 300 degrees centigrade, oh, it is a gas. 1 atmospheric pressure and 200 degrees centigrade, oh, it is also gas. Okay, 0.01 atmospheric pressure and 100 degrees centigrade. See, 0.01 atmospheric pressure and 100 degrees centigrade, oh, it is gas. Right? And 0 degree centigrade and 0.001, like see that 0.001. Okay guys, let's see that 0.001, very small pressure. It's about vacuum. Okay, very small pressure, 0.001 atmospheric pressure and 0 degree centigrade, you will get steam. You don't need to boil 100 degree centigrade. Okay, either you should give the temperature or you should decrease the pressure. Okay, you decrease the pressure, pull that all of the pressure, make this vacuum and put the one water inside the vacuum, it will evaporate. Okay, so small pressure 0.001, your water at the 0 degree centigrade also it is vapor. It's not the liquid or not the solid more, it is a vapor at that time. Okay, that's why in the space, if you leave the water in the space, that's vapor, because space is vacuum. Vacuum has zero pressure, so it means it's vapor. Okay, so now that is temperature. Now minus 100 degrees centigrade, very small pressure also give you the solid. If the temperature there in the moon is minus 100 degrees centigrade, it will be solid. It will be solid. Your water will be solid. However, the pressure is small, but the water is solid. And what about this green boundary? At the boundary, for example, if the boundary point at this point, about let's say 0.001 pressure and this temperature, about minus 1 temperature and 0.001 pressure, it will be the mixture of the solid and the gas. Generally, let's understand this way. Okay, this is actually the two phases coexist. It has solid property. This your glass of water has solids property also, it has liquids property also. Because let's understand this way, some molecules, some portion will be liquid, other portion will be solid. So at that temperature, at the each boundary that happens. For example, what will happen here? This point is this is the point is 100 degrees centigrade, right? This point is 100 degrees centigrade. So that point is it has a liquid also, it has a gas also. That is the boiling point, right? So let's say that if this point, no, the 200 degrees centigrade, this is 200 degrees centigrade, right? 200 degrees centigrade and exactly this pressure and this 200 degrees centigrade, it is also a coexist, liquid, and this is liquid also. The half portion is liquid and half portion is gas. This is also a boiling point. So boiling point depends upon the pressure, right guys? At the 1 atmospheric pressure, you have the boiling point is 100 degrees centigrade. See? So 100 degrees centigrade is the boil. If you give the more pressure, your boiling point may be different. So look at that. At this point, you have the gas all evaporated. At this point, what is the pressure? You decrease the pressure. If you give the pressure more, let's see that your pressure is 1000 atmosphere, for example, at 200 degrees centigrade, still it will be liquid. 200 degrees centigrade, look at that. If you give the lots of pressure, still that will be liquid at 200 degrees centigrade. If you decrease the pressure up to 1 atmospheric pressure, 100 degrees centigrade, you have gas plus liquid, means that's a boiling point, right? And if you have a little bit more temperature, like 100 degree, 100.00001 degree centigrade, everything will be steam. And if 99.99 degree centigrade, it will be liquid. Okay, but after 0 degree centigrade, it never ever solid. You see that? Solid is below 0 degree centigrade. Water, in case of the water. So now this is another point that is said to be the critical point. That critical point, if you increase the temperature, increase pressure, you are increasing pressure and temperature. If you increase more pressure and more temperature also increase, pressure also increase, there is a situation arise at which, look at that, it is the mixture of the gas, it has both property. It looks like gas also, it looks like liquid also. It will be liquid of the gas, it will be the mixture of the gas and the liquid at that time. Generally what happens? This is your container, gas is here, right? Gas liberates, gas is above the surface, right? Gas is above the surface, here is the liquid. That happens, right? Liquid is down and above is the gas. So, but that don't happen in this point, mixture of the gas and the liquid. It's not like that. You can find a gas molecule also here, liquid molecules, liquid state and gas state, it merge together. That's why it has a property of the gas also, property of liquid also. Density is same as like the liquid, but the property is same as like the gas. Very strange. That is the supercritical fluid that is said to be. Okay, so that is said to be the supercritical fluid because the density is similar like liquid, but its property are same as like the gas. So that's why it is the superposition of the gas and the solid. Others are not the superposition. In the other case, if you boil the water in a container, you will see that below here are water. It's a boiling, it's splashing, it's boiling. This is the water. But the above here you can find out the steam. Here is water. Two phases are separated in certain temperature, but after critical point, no phase separation. Phase are mixed together. Okay, so look at that. In this temperature, phase separation. This phase is liquid, this phase is gas. At that temperature also phase separation, but here is phase mix. There, both are. So it is a superposition of two phases. Okay, so that's why it means that generally you should understand that it is a both property you will find. It is a mixture of liquid and gas. You can understand like that. Okay, but I would say that it's a superposition. It is a both property. So this is the phase diagram. So let's see phase diagram of the another substance like the carbon dioxide is also like that. Same as like, right? So this portion it is solid, this portion is with the liquid, that is its superposition. Supercritical fluid this is, right? This is a supercritical fluid. Here you have the liquid and the gas. This has the mixture of liquid and gas here, because that's the supercritical. Okay, so this is the way we finish the liquid state. And thank you so much. What is our takeaway in this videos? We have studied the property of the liquid and the solid, right? The vapor pressure, surface tensions, intermolecular forces, boiling points, right? They all are due to the intermolecular forces. And finally, we will study the phase diagram, and we also study the what are the phase separations and what are the different point on the phase diagrams, and how we will see the phase diagram. We will study in this video. Thank you so much. We will study. We will go to the next chapter in the next videos. Right now, bye bye. Take care. Best wishes. Thank you so much.